Good afternoon, this is Schweitzer. We're going to run a little video here on one of our trends, which is ionization energy. All right, so ionization energy is simply one of our atomic trends that they use to see if you understand the structure of the atom and really Coulomb's law. So we have a nucleus here that is radiating out Coulomb attraction or some sort of a tractor beam for electrons here. So it's pulling in things, and the more attraction you have here, which is based on Coulomb's law, which is force equals charge of the nucleus times the charge of an electron divided by the distance squared, then that's what we want to know. If I want to rip this electron off of here, then this attraction really is what I'm fighting off. Okay, so what is ionization energy, and how do I represent the ionization in a reaction? So this is the amount of energy needed to remove an electron. Now there are things we might call first ionization energy, second ionization energy, third ionization energy, and this is a situation where, okay, this is to remove the first electron, this is to remove the second electron, you remove 2 electrons, you remove 3 electrons, and so on and so forth. So ionization energy, ionization of an atom to its common ion. Now this is bringing us back to what's the most common form of this, really. This guy is aluminum plus 3, okay? So I want to remove 3 electrons, okay? So I'm going to do the first, second, and third one all at once. I could do several stepwise if I wanted to, remove 1, then remove 2, remove 3. So I could do, let's say, so aluminum goes to, let's say, aluminum plus 1. I'm going to do just this, remove 1 electron first. So an aluminum has 13 protons. So this guy has 13 protons and 13 electrons. So this guy's got 13 protons and 12 electrons. And here is the electron that you would do. Keep in mind this is oxidation. If I want to do all 3 at once, I would just do aluminum goes to aluminum plus 3 electrons. There you go. All right, so this guy's most common ion is F negative 1. In this situation, okay, I got 2 of them, so I'm going to produce 2 F negatives that will be separated, 2 of them. They're not connected as a group anymore. And I got to add 2 electrons to this thing because this thing has, the fluorine individuals have 9, so now each individual has 10. So I need to add an electron each of them, and that's 2 electrons. Sodium's most common ion is plus 1. So this is going to go at plus 1. And of course, it's losing electrons. So where did it go? It's right here. This is snapshot before, snapshot after. Add energy to each of the reactions above, signifying if the reaction is exothermic or endothermic. All right, so in this situation, anytime you break a bond, okay, that requires you to do something, right? You need to put energy into the system to break something. If you got a nucleus and you have an electron here, okay, this thing attracts naturally on its own. So if you're going to pull it away, I need to add energy to physically force this thing out. Force times distance equals energy, and that's really what we're doing here. So anything where you're breaking a bond, it'd be exothermic. If you're forming a bond, which means you didn't have to do anything, like a ball rolling down a hill, what do you got to do? I don't got to do anything. It just happens. And the ball is releasing energy, and it's going into the form of kinetic energy. It's starting to go faster. Now it's got all this kinetic energy now. You didn't do anything. It's rolling along. Runs into you, it's going to hurt. Now you got to take that ball and you got to lift it back up the hill. Okay, now you're giving it energy. This would be an example of exothermic. This would be an example of endothermic. Okay, so where are we breaking? Anytime we remove an electron, we're breaking an attraction. So that means I'm exothermic. I have to, so anytime I'm breaking something, I got to put energy in. Okay, so that's going to be an endothermic process. So oxidation requires energy. I'm going to put energy here, and I'm going to put energy here. Okay, and now I'm forming a bond. This means I have I have an electron. It just comes up here and sits in all by itself. I don't have to do anything. It just rolls over because of Coulomb's law is doing all the work for me. That's going to just become more stable and releases energy. And that is right there. Just like the ball rolling down the hill, it's becoming more stable and therefore less energy. Okay. So this is sort of a harbinger of things to come. Okay. This energy idea. So we're just introducing that. All right. Which one has the highest ionization energy? Lithium or cesium? Now, the last chapter we talked about our general thought process. Okay. The general thought process is all based off Coulomb's law. Force equals charge times charge divided by distance squared. And because that distance has a square there, distance makes a big difference, way bigger than just the top numbers. Okay, if I double my distance, then this is 1/4 of the force. Okay, it's not proportional; it's exponential. So that's where our first rule comes in for energy levels. Energy levels really make a difference as far as you know, as far as distance is concerned, energy levels. So we're really looking at two things with energy levels. One, do you understand the atomic structure? And do you understand that Coulomb's law has this square here, which makes it an inverse square, which means it definitely has an effect. Coulomb's law. All right, and then 2 is number of protons, and then 3 is going to be, as always here, number of electrons. Okay, so and we've already talked about some of these explanations. We'll get to them more as we move along here again. But essentially now, what's really important about here is they said, who has the highest first ionization energy? Okay, well the lithium has 3 protons stuck inside here. And the cesium has lots of them. Cesium has 55 protons. 55 protons stuck in there. Okay? So in a sense, you could say, which one has the highest ionization energy? Now, you might say, okay, well, this one's got more protons, so it should be harder to remove electrons. This one's got less protons, so it should be easier to remove. But what we're looking at here is what what electron are we actually taking off? If I'm going to take off this electron and this electron, then yes, absolutely, this one's going to be way harder. But that's not what I'm doing, okay? I'm taking the outer electron off. This one versus this one. Okay, we're not really comparing apples to apples here. We're saying just remove the outside one. Well, this guy's way farther away. That's not fair. Doesn't matter. Okay, that's the first one that gets knocked off. The one on the outside. So energy levels is what we're looking at here. Which one's easier to remove? Okay. Which one has the highest ionization energy? Lithium has a higher ionization energy. Why? The electron is closer, and that distance has not a linear effect here. Okay, it's disproportionately closer, so it's disproportionately larger amount of energy to remove. Okay. So really, the distance plays a dramatic effect in this role here. All right, next one. Who has the highest ionization energy? Okay, now we're looking at sodium versus magnesium. Now again, you'll find that they have the same number of energy levels. Okay, same number of energy levels. So we got 1, 2, 3 energy levels. 1, 2, 3 energy levels. So no, our first energy level rule is out. All right, can't use that. Number 2, we're looking at number of protons. Now again, I prefer just use Coulomb's law. Use Coulombic attraction to explain this. Electrons are at the same distance, all right? But this guy just has more protons. So more protons yields more attraction, okay? More attraction. And therefore, a larger force is needed to remove the magnesium, right? not a huge amount, but some. Okay, because when you look at the force equals the Q over distance squared, yeah, this guy here is only has a little bit more positive here. So this is a little bit more. Okay, it's linear at that point. And therefore, I also mentioned that this guy is ever so slightly smaller. Why is it ever so slightly smaller? Because we got a larger nuclear attraction pulling on than this one does. So the distance is smaller, but just very little bit. Okay. All right. So the ionization energy is bigger, and that is opposite of size. Size here, this guy is smaller, ever so slightly, not a ton. Okay, and then moving along here, how do I justify or explain? Okay, we kind of talked about this a little bit. So with ionization energy, these two are probably the most common. You very rarely see this thing as referencing as far as ionization energy, but there we go. So we'll try it. Pause these, give them a whirl. Okay, so sodium versus sodium plus. The sodium plus is isoelectric with neon once again. So neon. Who's got the larger ionization energy? Okay, the neon does. Why? It's smaller. So that go just strictly off size. So the electron is closer to the nucleus, so it's got negatives there, but it's got closer to the nucleus, and therefore it's got a higher Coulombic attraction. All right, same number of energy levels. This guy is neon as well. Okay, so same energy levels. Number of protons are the same, electrons are the same. So okay, so now this is one where, you know, big misnomer. Oh, this is probably one of the biggest misconceptions that people make. Okay, who's got the looking just simply for ionization energy here? Doesn't say that ionization. This is just the hugest thing to try and break, and we do it ourselves. We're probably our own worst enemy here. But people are going to say, "Oh, nitrogen, full shell, more stable." That is a big no-no. Full shell. Okay. Do you see? Have we talked anything about this at all? No. Okay. We do not want to reference a full shell. What we want to reference is Coulombic attraction. Okay, if you reference a full shell here, I'm automatically going to mark it wrong. We do not want to do that. Okay, so who is it more difficult to remove an electron from? First things I would mention to you is that it's not this guy. Okay, this is the one that's more difficult to remove electron from than this one. Okay, few things you could possibly reference as you remove, okay, additional electrons, okay, it gets harder. It gets increased ionization. Now again, I like to think of it as if you have a nucleus and you have electrons here, then what I do is I remove one, less electron repulsion, I get a little bit closer. Therefore, this one's going to be harder to remove. I have the same number of protons. Okay, that's how I explain it. Someone else might, I've seen it acceptable on AP tests to say that, oh, well now the overall atom has a positive 1 charge because I removed one. So therefore it's more difficult to remove a negative from something that's positively charged. I don't like that, but they take it. So just the opposite, if I'm adding electrons, okay, it's just going to get it's going to get harder and harder to remove electrons going this way. So -2 would be a little more difficult to remove one from, -1 would be a little more difficult to remove from, neutral would be a little more difficult to remove from. If it were positive, it'd be even harder. So removing successive electrons always gets more difficult. Okay, always gets more difficult. All right, in this situation, so do not reference a full shell. Go back to our rules. We actually just did this one right here. Okay, and I would reference the size, literally the distance from you have the same positive and the same negative. So just what's the only thing different here is size. And the electrons are a little bit farther apart because of electron repulsion, and therefore a little easier to remove. All right, nitrogen versus neon. All right, so same energy level. Protons. This guy's got more protons, so it's more difficult. More protons here, more difficult to remove. All right, we got nitrogen -3, nitrogen again, same number of energy levels. This guy's isoelectric with the neon. So same energy level, more protons, harder to remove. Now again, we get the full shell here. That doesn't matter, okay? That's really doesn't matter. All right. All right, ionization energy, the amount of energy needed to remove an electron. Okay, what's our actual trend? Okay, so for the size of the atoms, we know, I'm going to do different colors here. So let's do size first. All right, let's do this guy. All right, so size we'll do in blue. And so size increases as you go down this way, and it increases as you go this way. So this is my biggest atom right here, francium. And then let's go with, let's say, red here for ionization energy. And so this is ionization. And we know that as atoms get bigger, electrons get farther away, it's easier to move. So it doesn't matter. Size is the thing. Farther away, it's easier to move. So the ionization energy gets bigger as you get smaller. And again, bigger as you get smaller. That's the main deal there. Okay, or smaller as you add more protons. So ionization energy increases the upper right-hand corner versus, let's say, the size gets bigger as you go to the bottom left-hand corner. They're never going to ask you these trends, but sometimes if you have this trend in your head, then you can use it to backtrack. Say, okay, why is this happening? You'd never, ever, 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 never, ever, ever, ever use the periodic table to justify something. You just absolutely cannot do that. Okay? You can't say that francium has a smaller ionization energy than lithium because it's lower on the periodic table. That is a rookie mistake there. You do not want to do that. Okay? All right. Nitrogen has a greater first ionization energy than oxygen. Explain this. Okay, let's find them first of all. So nitrogen is here, and oxygen is here. Okay. So they're saying that nitrogen has a greater first ionization energy than oxygen. So our trend here, now again, remember, there are two ways they can do these types of problems. Number one, they can give you a trend that follows what you're supposed to be seeing. And then you need to go to it, just explain what we normally would do. Okay, you'd say, okay, these are the rules we just learned, and you'd want to explain them. Sometimes they'll give you something that's not working. Remember, these are trends. They're not always working. They could say, okay, this is something that's happening. We see it, we measure it, explain it. So you'd want to go back to atomic structure and say, okay, is there something in the atomic structure that's changing right there that could be causing some variation here? Okay. Now they're saying, now which one are they doing here? Nitrogen and oxygen. So in this case, same energy level, number of protons. This guy's got more protons. So going to the right, it's getting smaller. Sorry with the pencil, smaller, and therefore ionization should be getting bigger as you go to the right. But they're saying, oh, hold on a second. Turns out in nature, nitrogen's bigger. Okay, so which of these could possibly explore this anomaly? Okay, we haven't done anything with electron activity yet. The nitrogen atom is smaller than the oxygen. Technically, no. Oxygen's smaller. The ionization energy, the electron ionized from nitrogen, so the removing electron, experiences less electron repulsion than the electron ionized from oxygen. If it's got less electron repulsion, remember this is what's gonna kick the electron away. So if there's more electron repulsion, it would literally, okay, so you have electron, you have the nucleus. Okay. If it experiences less electron repulsion, then it would be more difficult to remove. So this one possibly could work. Let's check this one out. Electron ionized from the N2 was an S2 electron, No. The S2 is the um, is a higher energy electron, so it would not be the first one to be removed. So this one definitely is out. So the electron, S electron, while the electron ionization from the oxygen is a 2p, they're both 2p's. All right. So that one's out for sure. So sometimes on these guys, you gotta read them all and eliminate ones, and then pick the one that's the best. All right. Kind of an older sort of style question. So but just kind of ask yourself a little bit of these things, and then you can check it out, and then find them on the periodic table. That's what I would do. So find each piece, calcium, silicon, and then you can just go ahead and order them by our rules. Should have an answer here. I don't. You can go ahead and check your own. All right, so can I remove multiple electrons? We talked about this already. So this is a classic question here. Okay, they're going to give you data, and you're going to have to analyze that data. Okay. So in this case, typical question, atom has 3 electrons removed. The following data was collected during ionization. We got this energy, also another energy. So if you look at this, you must see, okay, we know that successive electrons, it always gets more difficult to remove. And the question might be, okay, that's fine, but look what happens to this guy, okay? It is way, way, way bigger, okay? So something happened between these 2 points here. So likely at this point, what you want to get out of this is that we have our nucleus, and I have electrons here. What I'm getting from this is that the first two were from looking like this. They're at 1 energy level. But the third one must have been much closer. So the atom that we looked at here must have only had 2 valence electrons. So it came likely from the second row of the periodic table, or the alkaline earth metals. That's a super common question. There we go. Look at the big increase. What element is this? And it could be on a multiple choice type problem. It could be magnesium. It could be anybody in that family. Okay. Notice here on this trend here. Okay, how much the first, second, third element. Okay, the ionization energies, how they change. The sodium has a big bump after the first one. Magnesium, big bump after the second one. Aluminum, big bump after the third one. Why is aluminum big bump? Because aluminum's got 3 valence electrons. So I'm pulling from a much closer electron. So Coulomb attraction goes nuts. All right, look how big these differences are. Okay. All right, here's an actual example. Take a moment, take a look. Okay. Give an answer for this guy. So what do we got here? So a big jump after the third one. So this guy's got 3 valence electrons. Let's just do aluminum. X. Okay. 1, 2, 3. Okay. So which of these guys is X? Likely in the aluminum family. So it's one of these two here. It's not nitrogen. And why? Because it has 3 valence electrons. There we go. All right. And that's the end of our little presentation. Thank you.